So what are numbers? Well, the definition goes they are mathematical symbols used to count, measure, and label objects. So, for example, this dude here, his name is Frank. So Frank asks, how many objects are there? Like we know there are four objects, but the Frank is not familiar with the number system yet. He doesn't know what exactly number are and how we can use them. He have no knowledge of counting, and thus we need to enlighten our friend Frank to know, to answer his questions, that how many objects are there. So let's move. Oh, there are XXX objects. That's his way of counting. Clearly, he don't know about symbols that are used to denote the counting. So he's created a special symbol XXX for these four objects. Well, now we have added some more objects. Now we have in total 8 objects. Well, Frank here again asking the question, how many objects are there? Well, again, he came up with the second symbol. He said there are Y, Y, and Y objects. Clearly, that's something he devised himself, and as of now, he has no knowledge of the numbers, symbols which are used for counting. So this is going to play this game forever. The game of labeling the different amount of objects. For example, he will say these objects, the quantities alkyl, and then he'll say quantity of these objects is KGL, and the last one it's KLM. Well, it might be helpful for him, for us it's not, and clearly it's not going to be helpful for him as well for a long run. Well, Frank dude clearly is frustrated and wants a better way. Is there a better way? And for your information, Frank, there is a better way, and that's number system. So what is a number system? Well, in simple words, a number system consists of set of symbols, each symbol representing a quantity of objects. Symbols are combined with each other according to some rules to get more meaningful symbols. And this makes sense to us, it might not for our newbie, Frank. So a number system consists of the set of symbols that we already know. For example, a decimal number system has uh, symbols going from 0 to 9, and you can combine them in a way to represent quantity, and that's what works. Well, for example, let's have a number system of these three symbols. And Frank here dudes want some example. Well, so X, Y, and Z are the three symbols of the number system. And we have defined here this constraint that Z will be greater than Y, greater than X, and Y will be greater than X. Based on that, we can say they are in increasing order. Now we define this quantity of object will be called X. This quantity will be called Y. This quantity will be called Z. Well, clearly, each symbol represents a quantity. Frank got that. Let's have a number system of three numbers. So yeah, we got it. Now, how this system that we defined here is going to be useful? Well, this is the unknown quantity that the Frank want to know in terms of our defined number system. So what the Frank will do is just divide this quantity in such a way that it will look like these quantities here. So he has divided this quantity into a Z quantity and an X quantity. that is defined in Z quantity and X quantity. And well, Frank seems uh, amazed by this idea, meaning we have Z quantity and X quantity. And in a similar way, any chunks of objects can be broken down into those fundamental quantities. So this one can be represented using Z, Z and Y. This one, Z and Y. Then we have Z and Y. And this one for the Z, 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 Z and X. Well, that's amazing. This solves the problem, no? Well, Frank thinks he has solved the problem. There are still some problems. How are you going to measure big quantity of objects? So if you have very big quantity, you are going to a very lengthy string, and clearly that's cumbersome. Clearly the string of symbol was increasing with quantity. All it's natural, but not very efficient. So to solve this problem, we can add more symbols in our number system. Well, for example, in this number system here, we have 5 symbols in increasing order given below. And with that, you can see the quantities they represent. This is X, Y, Z, A, and B. So the symbols that we have defined in a number system are representing these quantities. Now, this one here, this quantity of objects is represented by our old number system that we saw in the previous slides, which was using only 3 symbols, Z, X, and Y. So these, you can see the length of the strings here. Now, comparing it with the length of string given by our new number system, which we're using the additional symbols, you can see it's comparatively smaller. Well, there's also another way to solve this problem, and that is recursively quantifying the quantity of symbols. Well, so you have objects here, and you can quantify them using a number system using the symbols of them. But you can also quantify these symbols using the same number system, and you can apply this process recursively. So for example, this quantity of objects here, you can represent them using the string. So this is an old number system, Z, 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 and X. That's some lengthy string. Now you can treat this Z and X as objects. So you can say we have quantity of Z's and there's some quantity of X. And you can say the quantity here of these Z's is Z and Y. So this is Z and this is Y. And the quantity of X, well, it is X. So we have solved half of our problem, but the problem's still there, and it is a problem of reference. For example, the quantity of Z, here it is represented by this string, the quantity of X with this string. So the Frank will think, so the quantity is Z and X, Y by combining both of them. So by combining both the strings, Frank said the quantity is this. Well, which is the wrong answer, because clearly the quantity is not that. Because we are not referencing the objects for which we have measured the quantity. Because here the Z and Y, it represents the quantity of Z's and not the objects. Similar for X. But in this case, Frank can clearly misunderstood, anybody can clearly misunderstood that this whole strings, it represents the quantity of objects here, but not these symbols itself. So we also need a way to refer to objects, the quantity of which we are representing. So it goes like this, the notion goes like this. You have object and you have quantity in terms of another objects and symbols, because it's recursive. So which means you can represent this whole quantity of z's by using this notion. So here z is the quantity of z is this in the string. In the parentheses, you can see this string represent the quantity of z, while for x, it's x. So you have this object and its quantity, and that's the notion one should follow, because otherwise it will create ambiguity. So the correct answer is this: z has this quantity, x has this quantity. And so we know more precisely that object we are representing has this quantity, in which the z's symbols has this quantity, x has this quantity. This whole notion, this whole string can be has a shorthand, which is this. You can replace the and by the comma. So Frank seems satisfied with it. Frank got it. Let's move. So that way we can label any quantity object. That's so cool. I know, Frank, it's cool. So, but there is another problem here. So let's assume we have some sheep and farmhouse with a quantity this, and now we decided to add some more sheep in the farm, say m quantity. So now we are supposed to recompute the quantity of sheep in the farmhouse, which is cumbersome. Clearly, there is no such thing uh, as how the quantity will change as we add more quantity, and this this is called addition. We know there exist mathematical operations: addition, subtraction, multiplication, division. Frank doesn't know that. He just got to know that there exists this thing called number system that will help you count things and represent them. So Frank knows that, oh, it's really tiring. So clearly we need a solution for that as well, and then we know that's fall under the addition. So how will you add two uh, the strings that represent your quantity? So two strings of quantity, how will you add them? Well, Frank has no idea, but we do. So for example, first we need to define something called atomic addition. That is, if you add an x quantity with x quantity, you will get a y quantity, and that's true. If you have one object, another object, you will have two objects, and 2 is represented by y. And if you have y object and x object, then you will have three objects in return represented by g. Clearly, the notion of counting that we know, Frank doesn't know. So for Frank, we are going from bottom to up, right? Well, Frank actually got it before I even explained it. So yeah, addition. Here I'm going to explain how you are going to add two quantities. So here this is the first quantity, and this is the second quantity m, which is represented here. So you are going to add the quantity of corresponding symbols. So there are going to be only three symbols for any quantity, which are z, y, and x symbols. And recursively, they will have their quantity in this format. So we see that there is only z symbol in the first term, and there are two symbols in the second term, which are z and y, with the corresponding quantity. So we are going to add the z symbol quantity from both terms. They will be added, and the y will remain as it is, right? So down there here, you can see the z quantity, z final quantity, or you can see the z symbol with the final quantity in the parenthesis is coming from these two quantities, right? So you are going to add them. here it should be noted that the comma and plus they are same, right? So now we are going to add these two quantities. We already know that x and y, x summation of them, we already know it's y, right? So it's going to be y. So here x symbol with x quantity, x symbol with x quantity will give x symbol with y quantity, and it's reversible in this case. You don't have to do this reversing, but we'll explain in the following slides how it's true. Okay, so we got the summation of x and x into this symbol, into this quantity, and now we are left with again quantity of z symbols. So z of z and z of y, they are again editable. You can add them. So the final quantity of z symbol will be the quantity inside it, which is z and y, and this will give you final quantity here. Y will remain as it is throughout because there was no corresponding y quantity in the first term. So the final answer is this here. Again, the plus here is replaced by comma here. So I think Frank got it. He says he got it. So Frank now clearly can ask that can we do addition, subtraction, division in the same way? Well, we can do that. And in a similar way, the subtraction, multiplication, and division can be defined. So multiplication. So what is multiplication? Well, it definition goes how many times a particular is present is represented by multiplication. A particular thing, how many times it is present, it is represented by multiplication. For example, we have this well-known notion that is z symbol is z times, and that's what we just said when we define multiplication. So it means the multiplication form means z is z times, which means this form is already a multiplication form, and here z is being multiplied with z. And some atomic multiplications are these represent simply the commutative property of multiplication. So x symbol with x quantity will be x symbol with x quantity will be x. So you can omit the quantity of x because it is clear itself if it is not mentioned. Similarly, x symbol with y quantity is similar as y symbol with x quantity, and which is same as y. You can omit the quantity of y which is clear itself, that is the y is only present one time, and similarly for the third case. So the some cases that should be mentioned here are these two, which is y quantity z time can be written as the z and z, which is the z symbol x times and the z symbols x times. Here x is omitted, which is clear itself. Similarly for y mean y symbol y times can be written as the z symbol and x symbol. And clearly it is provable here, that is y here is 2, z3 gives 6, and this z plus z which is 3 plus 3 which is also 6. So yeah, it is true. Similar for the last case. Well, Frank says it's interesting. It is. So multiplication properties. So some properties that you should or supposed to keep in mind, because the following slides are going to need them. This is the distributive property of multiplication. In addition, this is the commutative property. Very easy to understand. Also, there is a shorthand notation. So if you have a a which is multiplied with a which is multiplied with a up to n times, then you can represent it using the a power n or a cap n. Well, with that, let's move to very important part, the standard form. So let's say we have a quantity, and this is the quantity with z symbol as this quantity, y symbol as this quantity, x symbol has this quantity, and combined they're representing this q quantity, right? So this whole equation, this whole quantity, it can be represented as this, in this format. It can be represented using these properties. So you can use the property of distribution and can represent it this way. Further, you can see you can reduce this y square, right? Y square with this z and x. So we just defined here, this is the y square here. Y square can be replaced with z comma x. So we did in a comma is simply plus here. Further, you can do the distribution of z. Here we have z, two z's, which means one is z quantity x times another z quantity x times. So the quantity will be added. So x plus x, which is y. So x plus x, which is y. And similarly for this normal x. So well, Frank seems to comprehending this and taking time for. So we understood how this format can be converted to this format here. Up to here we understood it, right? And by further reducing it, so here you can combine these two, z symbol with the x quantity, y quantity. The quantity will be added x plus y, going to give you z, and z into z will be z square, right? So, and here you can see we have z square with y quantity, z square with x quantity, right? So you can add the quantity x and y, you will get z, and z with the z square in multiplication will give you zq. The first term is going to be as it is throughout the whole process, and finally you will have this equation here, this form here. This something very interesting about this equation. So now you can see clearly that for this quantity we performed some sort of reduction process to reduce it to this format, a standard format. In this format, each term is some form of a and z raised to power something. Each term is in this format, where z is actually the highest quantity. That is, z represents the highest quantity in our number system, while the coefficients which are being multiplied with the z's power, they are always less. So we can standardize about it, that any quantity, it representation, it can be boiled down into the following format, that is ai and zk. So it will be the summation of these type of terms, where the k is going from n to 0. So For the zk, k is going from n to 0, and the coefficient which is being multiplied with it, ai, I is going to 0 to n, right? So in this format, you can convert any quantity. So ai represents some atomic quantity here, which will be x or y, and here x and y are less than z. So if you are using some other number system which have a, x, z, b, and a, some other symbols as well, then the z will be the highest symbol, the symbol which represent the highest quantity, right? And the ai symbol, it comes from the set, the whole set of symbols except the highest symbol. So highest symbol will be not present. Well, here the Frank asks very interesting question, a very good question actually, that all terms should be present. Clearly we saw that in this case all terms, that all powers of z were not present. Z of 1 was not present, right? Z to the power 1 was not present. So in this form, we said that these terms, the power of z, they can be omitted, because a will always be some quantity, which means all the power of g will be present. But in this case, that didn't happen. Not all powers of z were present. And for that matter, well, Frank, that was an interesting question, because it is not mandatory for all terms of the form aizk present, right? So not mandatory for all terms to be present. And to make sure that this happen, we actually need to define a quantity called null quantity, and actually present it should be present from this evidence here, right? So from the fact that 0 1 was not present, which means there was some quantity there which was null, thus nullifying the power of z's, and thus comes the null quantity. So null quantity is simply no quantity. So for example, you have some box here with one object, you will say it is some quantity, because the box has some quantity, might be 1 2 3 objects, but it has some quantity. The second box here has no quantity, so you'll say that it has null quantity. So we're going to add a new symbol in our number system, and that will be a null symbol, which represents the null quantity, which simply means 0. We already know that. So finally, I will disclose the formal definition of number system. So we'll start with any set of atomic quantities. Not any, but there will be some constraint on it. So like we have quantities x, y, z. These three quantities are atomic. Or we can have x, y, z, a, b. We have in total 5 symbols, each representing an atomic quantity, right? In a similar way, x, y, z, a, b, c, d, and so on. Each system that you're defining should have a null symbol, right? So in general, if you have n plus 1 symbols from S0 to Sn, they should follow the following property. The first property is from S0 to Sn, they should be in increasing order. So S1 will be greater than S0 and S2 will be greater than S1 and so on. So by that matter, Sn will be the highest element, right? So second property is S0 is supposed to be null object or null symbol, right? When it should represent no quantity S0. The next symbol S1 should be a unit object and Sn should be a base object. Now there is something special about them. For S0 it's that it is representing no quantity. For Sn it's that it acting as a base object. I mean, the power, if you represent any quantity using the number system, the maximum element, it is going to be present in this format, d to power k, and some coefficient will be present, right? So it's special definitely. And S1 is a unit object and its speciality is given by third property, that is the adding this unit element or unit symbol with any object from S0 to Sn minus 1. Here I'm excluding the Sn, right? So should keep in mind. So from S0 to S minus 1, if you add unit element, unit object in those symbols, then you get the next symbol, right? So if you're going to add unit element in this S1, you will get S2. If you're going to add an S2, you're going to get S3, right? So this equation with this constraint, right? So we can write the quantity in standard form using the above set of symbols, right? Here should be off set of symbols. So we have the terms in the form A, I, B, K, right? And B is here the largest symbol, which is represent the maximum quantity or highest quantity, right? AI can take the value from S0 to Sn minus 1. It is given by this constraint here, right? So AI will be Si, but Si should be less than B. So any quantity can be represented in this format. And now, since AI, AI, you can also take null value, right? S0. So which means you can also omit the A powers. Now, this whole system, it does capture what we just obtained here by reduction, right? And it does the problem of this question that all terms should be present or not. And clearly, with the null quantity, we can achieve such an effect with some additional properties, some uh, in very formal terms, we have defined these properties, and With that, we have a number system that can represent any quantity in a standard format, right? So also any quantity can be represented as, so you can see the equation here. It is in the format like we discussed in the previous slides, ai and b power k. But still it's not very convenient to represent a quantity, so we'll exploit this pattern of b power, right? The power of b going from 0 to n, right? 0 to n, and we can label them as positions. So first position is 0, second position is 1, third position is 2, up to so on. We have the nth position, and in those positions we will place the coefficient of the corresponding powers. So if the v0 means b has power 0, we can place the corresponding coefficient of power 0 in that position. So here we'll have an, right? And in the one position, which is b raised to power 1, we'll have its corresponding coefficient, which is an minus 1. In a similar way, for the nth position is b power n, will have a 0 coefficient, right? So this is more convenient to only and only write the coefficient as how and where you are placing them. For example, in this case, an minus 1 up to so on is 0. And if you know the base, this form is very convenient to write any quantity rather than also including the base in multiplication with those coefficient, because the position of that coefficient will itself tell you that you are supposed to multiply this coefficient with the base to the power of whatever position your coefficient is at. And using this clever trick, this clever way of writing, clever way of uh, doing things, right? So we can have a convenient form. You can see this is the convenient form for this. So for example, we have this quantity. So z symbol with this quantity, y symbol with y quantity, x symbol with x quantity, right? Can you reduce? It can be reduced to this format, right? Standard form. And since we know our number system was x, y, z, z with the highest quantity was a base, and they were also null, which was the 0 element. So we know that we are working with the base z number. Although it's not mentioned here, it should be mentioned with a subscript z, right? And so you can only you are only required to place the coefficient of the base powers, right? So this whole format, it simply represents that y is the coefficient of the base, which is z, and the position of the y, which is 0. And you can add with it the second term. So we have null object, which should be multiplied with the base, which is z, to the position of n, which is 1. And in a similar way for the x, and a similar way for the y. So this is the standard form, which can be further represented in this format. They are the same. So, and this is also same. So it depends upon the convenience, and you can choose this format, which is very inconvenient, this which is relatively convenient, and this which is very convenient and used present day. Okay, so the power of the base, it represents the position, and the coefficient of the bases is placed on the position. If there are no coefficient for that position, we place the null object, right? So, well, I think the dude got the answer, is saying amazing. So, base 10 number system, this is what we are familiar with. The base 10 number system, we have symbols like 0 to 9. You call them numbers, right? And so you can represent the quantity in these forms: 100, 230, 111. They all are numbers, right? And in this number system, in the base 10 number system, we have 0 as a null quantity, null object, null symbol, 1 as a unit object, and 10 is the base object. And it is a number system that you are most familiar with, and you use it all the time for counting. Well, thanks. I hope you got to know what numbers are, why we need them, and I think the Frank also got his answers. Thank you.